In-place matrix transposition. In-place matrix transposition, also called in-situ matrix transposition, is the problem of transposing an NXM matrix in place in computer memory, ideally with unbounded additional storage, or at most with additional storage much less than NM. Typically, the matrix is assumed to be stored in row major order or column major order, i.e., contiguous rows or columns, respectively, arranged consecutively. Performing an in-place transpose in situ transpose is most difficult when i.e. for a non-square rectangular matrix, where it involves a complicated permutation of the data elements with many cycles of length greater than 2. In contrast, for a square matrix n equals m, all of the cycles are of length 1 or 2, and the transpose can be achieved by a simple loop to swap the upper triangle of the matrix with the lower triangle. Further complications arise if one wishes to maximize memory locality in order to improve cache line utilization, or to operate out of core where the matrix does not fit into main memory, since transposes inherently involve non-consecutive memory accesses. The problem of non-square in-place transposition has been studied since at least the late 1950s, and several algorithms are known, including several which attempt to optimize locality for cache, out-of-core, or similar memory-related contexts. Background. On a computer, one can often avoid explicitly transposing a matrix in memory by simply accessing the same data in a different order. For example, software libraries for linear algebra, such as BLAS, typically provide options to specify that certain matrices are to be interpreted in transposed order to avoid data movement. However, there remain a number of circumstances in which it is necessary or desirable to physically reorder a matrix in memory to its transposed ordering. For example, with a matrix stored in row major order, the rows of the matrix are contiguous in memory and the columns are discontiguous. If repeated operations need to be performed on the columns, for example in a fast Fourier transform algorithm, e.g. Frigo and Johnson, 2005, transposing the matrix in memory to make the columns contiguous may improve performance by increasing memory locality. Since these situations normally coincide with the case of very large matrices which exceed the cache size, performing the transposition in place with minimal additional storage becomes desirable. Also, as a purely mathematical problem, in-place transposition involves a number of interesting number theory puzzles that have been worked out over the course of several decades. Example: properties of the permutation algorithms. The following briefly summarizes the published algorithms to perform in-place matrix transposition. Source code implementing some of these algorithms can be found in the references below. Accessor transpose. Because physically transposing a matrix is computationally expensive, instead of moving values in memory, the access path may be transposed instead. It is trivial to perform this operation for CPU access, as the access paths of iterators must simply be exchanged. However, hardware acceleration may require that still be physically realigned. Square matrices. For a square NXN matrix n m equals nm, in-place transposition is easy because all of the cycles have length 1. The diagonals nn or length 2 the upper triangle is swapped with the lower triangle. Pseudocode to accomplish this assuming zero-based array indices is: for n equals 0 to n2, for m equals n plus 1 to n1, swap n m with m, nn them nn. This type of implementation, while simple, can exhibit poor performance due to poor cache line utilization, especially when n is a power of 2 due to cache line conflicts in a CPU cache with limited associativity. The reason for this is that, as m is incremented in the inner loop, the memory address corresponding to an m or m and jumps discontiguously by n in memory depending on whether the array is in column major or row major format, respectively. That is, the algorithm does not exploit locality of reference. One solution to improve the cache utilization is to block the algorithm to operate on several numbers at once, in blocks given by the cache line size. Unfortunately, this means that the algorithm depends on the size of the cache line it is cache-aware, and on a modern computer with multiple levels of cache it requires multiple levels of machine-dependent blocking. Instead, it has been suggested Frigo et al. 1999 that better performance can be obtained by a recursive algorithm. Divide the matrix into four submatrices of roughly equal size, transposing the two submatrices along the diagonal recursively and transposing and swapping the two submatrices above and below the diagonal. When n is sufficiently small, the simple algorithm above is used as a base case, as naively recurring all the way down to n equals 1 would have excessive function call overhead. This is a cache-oblivious algorithm, in the sense that it can exploit the cache line without the cache line size being an explicit parameter. Non-square matrices following the cycles. For non-square matrices, the algorithms are more complicated. Many of the algorithms prior to 1980 could be described as follow-the-cycles algorithms. That is, they loop over the cycles, moving the data from one location to the next in the cycle. In pseudocode form, for each length-owned cycle C of the permutation, pick a starting address S in C, let D equals data at S, let X equals predecessor of S in the cycle, while X SSSSSS move data from X to successor of X. Let X equals predecessor of X, sur of X. Move data from D to successor of S. The differences between the algorithms lie mainly in how they locate the cycles, how they find the starting addresses in each cycle, and how they ensure that each cycle is moved exactly once. Typically, as discussed above, the cycles are moved in pairs since S and Mn1s are in cycles of the same length, possibly the same cycle. Sometimes a small scratch array, typically of length m plus n, e.g. Brenner, 1973, Kate and Twig, 1977, is used to keep track of a subset of locations in the array that have been visited to accelerate the algorithm. In order to determine whether a given cycle has been moved already, the simplest scheme would be to use OMN auxiliary storage, 1 bit per element, to indicate whether a given element has been moved. To use only OM plus n or even log mn auxiliary storage, more complicated algorithms are required, and the known algorithms have a worst-case linearithmic computational cost of OMN log mn at best, as first proved by Nuff-Fish et al. 1995, Gustafsson and Swartz 2007. Such algorithms are designed to move each data element exactly once. However, they also involve a considerable amount of arithmetic to compute the cycles and require heavily non-consecutive memory accesses, since the adjacent elements of the cycles differ by multiplicative factors of n, as discussed above. Improving memory locality at the cost of greater total data movement. Several algorithms have been designed to achieve greater memory locality at the cost of greater data movement, as well as slightly greater storage requirements. That is, they may move each data element more than once, but they involve more consecutive memory access, greater spatial locality, which can improve performance on modern CPU that rely on caches, as well as on SIMD architectures optimized for processing consecutive data blocks. The oldest context in which the spatial locality of transposition seems to have been studied is for out-of-core operation by Altop, 1975, where the matrix is too large to fit into main memory core. For example, if D equals GCDN, M is not small, one can perform the transposition using a small amount nm/d of additional storage with at most 3 passes over the array. Altop, 1975. Dow, 1995. 2 of the passes involve a sequence of separate, small transpositions which can be performed efficiently out of place using a small buffer, and 1 involves an in-place dxd square transposition of. n m slash d 2 backslash display style nm slash d2 blocks, which is efficient since the blocks being moved are large and consecutive, and the cycles are of length at most 2. This is further simplified if n is a multiple of m or vice versa, since only one of the two out-of-place passes is required. Another algorithm for non-coprime dimensions, involving multiple subsidiary transpositions, was described by Catanzaro et al. 2014. For the case where an m is small, Down 1995 describes another algorithm requiring an m, min-nm additional storage, involving a min-nm square transpose preceded or followed by a small out-of-place transpose. Frigo and Johnson 2005 describe the adaptation of these algorithms to use cache-oblivious techniques for general-purpose CPU relying on cache lines to exploit spatial locality. Work on out-of-core matrix transposition, where the matrix does not fit in main memory and must be stored largely on a hard disk, has focused largely on the n equals m square matrix case, with some exceptions, e.g. Altok, 1975. Recent reviews of out-of-core algorithms, especially as applied to parallel computing, can be found in e.g. Sugg and Prasanna 2002 and Krishnamurthy et al. 2004.